Okay, so here we have the alkaline halide structure. And so the key thing that we want to take in consideration, the bond length of the alkaline halide is going to be affected by which halide we're actually using. So if you take a look and we think about it logically, which halide is going to have the strongest electronegativity? Fluorine. So because fluorine is going to have such a strong electronegativity, it's going to be pulling itself closer to that, pulling itself and that carbon closer together. So, and then also if we think about the size of fluorine, fluorine is considerably smaller than iodide, right? So that's also going to be a factor as well, because that radius isn't going to be as much. So the bond length between the carbon and the fluorine is going to be smaller than what we see with the bond length with the carbon and the iodide. Okay, and that's going to be because it's a combination of both the size of the atom and then also the strength of the electronegativity. Okay, since they're sharing those electrons. Okay, so then we sit there and we think about that bond length. And that bond length is going to have a slight effect on how the structures can be formed, right? Because if you have hydrogens on every part, and then all of a sudden you have a fluorine, that's going to affect, right? It's going to have an effect on the behavior of things. Does that make sense? You guys are all with me there? So we still want to take in consideration that electronegativity, okay? And then also the size, you know. Okay, so that also means that when we sit there and we think about it, where things are going to attack and where things are going to be able to occupy. Now, when we talk about water, right? So you guys remember water has polar moieties associated with it. So let's see. Okay. So if we look at alcohols, right? Alcohols are going to have very similar moieties that are going to be associated with it as well too, because of that oxygen, right? So alcohol structures are going to resemble water. So this here represents that carbon chains, so those hydrocarbon chains. So in this sense, it's going to resemble water. So it's also going to have those polar moieties. So we know that this guy's going to be your partial positive, and this guy's going to be your partial negative, right? Same thing is going to be happening here, partial negative, partial positive here, okay? And then so this other guy is also going to be associated with some of that partialness as well, because oxygen is going to be pulling. But that pull is going to be more seen with the hydrogen compared to the long carbon chains. Does that make sense? So like, even though that carbon is fairly weak in terms of electronegativity, it's only like 2.6, where hydrogen is 2.4. So the difference is like 0.02, right? So even though that it's fairly weak, just that little bit it has, and also the extent of the hydrocarbon chain will play a part in that, right? So the ones that are smaller are going to end up being more polar than the ones that have that polar part of it and the non-polar part of it. Does that make sense? No, it doesn't. It actually makes it less in that sense, because okay, so for instance, let's say we're talking about methanol and ethanol. Methanol and ethanol are both short carbons, right? So if we take a look at methanol, let's draw it up on the board. Okay, this is our methanol, right? So if we really look at it, it has the same two lone pairs, right, as we have here with water. Now, even though this here is a carbon, right, that carbon is being surrounded by those hydrogens and everything like that. It's going to have less polar effect of it because it's non-polar, right? Okay, so this component is nonpolar, where this guy still has polarity associated with it, this one arm, and this one also has polarity associated with it. This one doesn't have any polarity associated with it. Does that make sense? Or less polarity. Okay, so as that chain grows, as it gets bigger, this is going to be more nonpolar, right? You're only going to have one polar head, right? So in terms of polarity, overall, it's going to have less polarity than, let's say, the water does. Does that make sense? Okay. And so as the longer that carbon chain goes, the less polarity you have. But they're going to be interacting with each other because they're going to use dispersionary forces. And so the dispersionary forces are going to play a part. Okay, we'll talk about that here in a second. Okay, and so here they're just basically showing you the electrostatic map of methanol. And so you can see here, this part is polar, this part is non-polar, right? The red representing the more polar it is, you know, and then over here, the green, the more neutral it is. So. Okay, now here's ethers. Oops, clear. I want to keep my water though. Okay, now ethers. Okay, so they're going to kind of resemble water as well too, but in this case, less polar, right? So if we think about water is going to have more polarity associated with it, the ether is going to have less polarity associated with it. And then if we went in terms of how things are, we have water, we'll have alcohol, and then we'll have the ethers in terms of polarity, right? Of the whole system. Does that make sense? So like here, we have two carbon chains. We no longer have that hydrogen here, right? So we have carbon chains here. So you have two polar ends. You have something that's polar in the middle and then two polar ends on the outside, right? The longer those polar ends get, the less polarity we have. I mean, the longer those non-polar ends get, the less polarity we have. I spoke. Okay. So as these carbon chains get longer and longer and longer, it's going to be less polar, right? Does that make sense? Are you guys with me? Okay. Kayla, are you here? Are you here? Are you with me? Okay. Abby, Gracia?
Yes. Yes, I'm here.
Okay, so like for instance, here we have oxygen. Let's say we have, so this is ethyl ether, diethyl ether, right? Okay, so in this case, or this is also called ether ether. In this case, you have some polarity. It's all going to be focused here, right? With the oxygen. So this guy's going to have that partial negative, and then that carbon, that first carbon is going to have that partial positive, right? But we know that those are also surrounded by the hydrogen. So they're going to be kind of masked by the hydrogen, right? It's not going to be to the same extent as water is, you know? So water is going to have more polarity. This is going to have some polarity, but it's going to be not as polar, okay? So what are some of the effects that you guys think would be associated with that? Knowing what you guys know about intramolecular forces. It's going to affect their boiling points. Yeah. So are their boiling points going to be higher or lower? And well, you tell me. In comparison to water. So what would we expect diethyl ether to be compared to water? What do we expect it to be? Its boiling point higher or lower? So why do you say lower? Okay. Okay, so because it has less polarity associated with it, we'd assume that it's going to be lower, right? And then the reasons why we're going to say that, because water, we know, is being held together by those polar forces, right? That's partially positive and partially negative, where these guys are weakly partially positive and weakly partially negative, and relatively speaking. So we'd assume that it's going to be lower, right? And that's what you guys are going to see when we start talking about that. So in other words, if we look at our structure, the structure looks very similar, but it's going to behave slightly different because of the polarity of the structure. Does that make sense? Okay. So, yeah. So as we do the same thing with the amines, so we know that ammonia looks like this. H is here. Okay, so as we look at the amine structures, right? So a primary amine, right, is going to look almost like ammonia. It's going to have very similar polarity. It's going to be a little less polar, right? Because you have that carbon chain. Same thing in this case, right? Because we know that those are non-polar. So, and then in this situation, it's going to look less like ammonia. It's going to behave, I mean, it looks like ammonia, but it's going to behave less like ammonia, right? Because you're surrounding the nitrogen by the carbons, okay? And as the carbon chains grow, they're going to become less and less and less polar. So if you kind of take a look at these regions, right? Bigger region here, a smaller region, right? Although they're not joined very well, a very small region compared to the rest of the moiety, right? So this, again, represents non-polar. The red represents our polar component. Or the electrostatic. Okay. Okay, so this has a huge effect on boiling points. And then the things that you want to sit there and think about, those London forces, right? So those dispersionary forces, the longer your chain are, the more dispersionary forces you're going to have. That's going to affect your boiling point, right? The longer your chain is, your boiling point is going to be higher than compared to something that's going to be a shorter chain. Compared to something that's going to be a shorter chain, it's going to be a shorter chain. Now, if there's dipole-dipole interaction or polar interactions, right? So in that case, then that's also going to affect our boiling point. The more polar interactions you have, the stronger it's going to be. So that means your boiling point is going to be a higher boiling point. Right? And then hydrogen bonds. Hydrogen bond would be stronger than your dipole, right? So that's going to be even stronger. So that's going to be an even higher boiling point. So water is going to have a really high boiling point compared to some of these other guys. Does that make sense? And we know that the boiling point of water is what? 100 degrees Celsius. Okay, so let's look at this. Okay, so here are the boiling points. So methane, what does methane look like? What is the chemical formula for methane? What about ethane? Okay, propane. And then as we would go on, so if you notice, methane boiling point is negative 167.7. So we know that at room temperature, it's a gas already, right? That's why it farts. Yeah. Okay. So then we have ethane, which is negative 88.6. So all of those at room temperature are going to be gases, right? All of these guys are going to be gases up until the point room temperature is roughly 23 degrees. So after butane, right? All of these guys are going to be gases. Here we get into some of our liquids, right? Okay, so London dispersionary forces are basically induced dipole. So even though we have those hydrocarbons, right? That the carbon is only a little bit higher than the hydrogen. But even though it's a little bit higher than the hydrogen, it causes what we would phrase as the induced dipole. So it slightly changes it, right? And then so it can be picked up or induced by just the actions of what it's in, right? Or with itself. So partially positive, partially negative, partially positive, partially negative, partially positive. But this switch of partially positive to partially negative is what's happening. It's an induced moment. It's not something that's going to happen consistently. The fact that the electron is moving from one place to the other, being shared evenly, is going to be what's inducing that. Does that make sense? Okay. And so we got to think about it always as the electron constantly moving. Okay. Where in the case of water, the electron is constantly moving, but the electron is spinning about 90% around oxygen, and then only, that 10% around hydrogen, right? So then that seems like it's completely charged on the oxygen, where the hydrogen doesn't seem that. Okay, even though that they're sharing still. Okay, so does that make sense? Okay, so as that surface area grows with that molecule, you have more and more spots for that induced dipole. So you have more and more area for things to be touching each other and being induced, connecting together, right? And so that's why as we get bigger, our surface area is getting bigger, as that chain gets bigger, right? And it gives more space for those forces to interact with each other. Okay. Is that cool? Got it? Okay, so let's see.
Oh, yeah.
Oh, yeah. Okay, so let's see. Let's say we had these three molecules. Let's say we have butane. We have diethyl ether. We have let's do butanol. And we have water. Okay, so we have these four items here. Which one is going to have the higher boiling point? Range it from highest to lowest. It may help to draw the structure. Let me add one more. Okay, get some answers for me. From highest to lowest, the one with the highest boiling point to the lowest boiling point. Got an answer? Let's see. So from high boiling point to the lowest boiling point. Okay. Okay. And then we'll discuss it afterwards. Okay. 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 Right. Okay. And where does water fit in there? Okay. Yeah. Okay, do you guys agree? What was that? Slightly different, only slightly different? Okay. So give me yours. Water. Sec, butanol. Then diethyl ether. And diethylamine. And then butane. Okay. Okay, so those are, anybody want to else add a different list? And then we'll discuss it. Come on, we need at least 3 so that you all agree with one of those 2. Let's see if I can get it so we can see everything. You agree with one of those 2? Okay. Mauricio, do you agree with one of those 2?
Mine's kind of like that second one.
Like the second one? Okay.
Yeah, except sec-butanol and diethylamine are switched.
Okay, so you said only thing you have the second one switched. Okay, so let me show. Oops. Okay, now I was just putting up questions from earlier today. Okay, so let's break this down. Let's look at the structure. You said the second one and the which one are switched?
Sec-butanol and diethylamine are switched.
Okay. Okay, now it's just okay, so these are your 3 choices, right? So let's look at the structures. What does well, we know what water looks like. Okay. What about sec-butanol? What does the structure of sec-butanol look like? I did 5, didn't I? 1, 2, 3, 4, 5. Let me fix that. One, two, three, 4. Okay. And diethyl ether. Okay. And we know what butane looks like. And then we have ethylamine. Got my H. Okay. So tell me, what type of forces are going to be interacting with water? What was that? Hydrogen bond. So you all said water was number one. Okay. What about butanol? It has one hydrogen bond and London forces. Okay. London dispersionary forces. Okay. What about the ether? Dipole, dipole. Okay. And then London forces, right? What about the amine? We have dipole, dipole, and London. Are you sure? Dipole, dipole.
No.
Well, you're right. London forces. It's definitely not London forces, right? And then you also have that dipole, dipole that'll be at interaction at this point. But is there anything else that will be added on? Hydrogen bond. Yep. So that guy would have a hydrogen bond. Okay. And then the butane. What's happening in the butane? London. Okay. In terms of priority, who is the strongest? Hydrogen bond. And then dipole, dipole, and then London forces. So we would assume water would be number one, right? Then you guys are right, because the hydrogen bond between the oxygen and the hydrogen are going to be stronger. I mean, it's going to be a stronger interaction, a stronger pull in the case of the oxygen compared to the nitrogen, right? So then your next one would be your sec-butanol, right? And then it would be your amine. And then it would be the ether. And then lastly, it will be butane. So it's this one, except. Do you guys see that?
So then it would be waters, the amine, ether, and then the butane.
Yeah, butane would be the last. Yeah. Okay. Good. Yeah. Yeah. Okay, so you guys remember what dipole-dipole interactions are? So that's that plus minus going on, right? Where you're getting that shift. Okay, dipole-dipole interactions are going to be stronger than our London dispersionary forces. So in the case of we had cyclopentane compared to tetrahydrofluorane, which is basically cyclopentane with an oxygen, right? So in this case, you can see, look at the boiling point. Higher boiling point in the case where you have the oxygen present because of that dipole-dipole moment compared to the London forces. Okay. Okay. So if we look at alkanes versus ethers versus alcohols versus amines. So you guys can kind of see that, right? So alkanes are going to be our least, then our ethers, then our alcohols are going to be a little bit higher, and then our amines are going to be between the ethers and the alcohols. Okay. Well, of course. I mean, well, the less you have, the easier it's going to take to boil it. But the boiling point is not going to be dependent on that. I mean, let me say, how do I say this? It's going to be, you have a temperature where it boils at, right? That boiling point is the point where you're getting disruption of those bonds, right? The energy is to disrupt that bonds. So the boiling point isn't going to be a function of how much you have, right? What's going to be a function of how much you have is how long you have to boil it. Do you understand what I'm saying? Because the more stuff you have to go through more stuff, right? Does that make sense? So if you keep it at that boiling point, right, eventually all of it's going to boil off. But if you have a whole bunch of it, it's going to take a lot longer than it would take. Does that make sense? Okay. Okay. So this is a good way of doing a comparison, right? So if we just change our little group, so if it's a hydrogen, the effect, and then as we go on with the halides, right? So hydrogen is going to be weaker than fluorine because fluorine is a little more electronegative, right? And then these guys are going to kind of make up for it because of their length, right? So like here we have hydrogen, fluorine, chlorine, and bromine and iodine. Because it got that length is longer, it's going to make, what was that? There's more surface area for it to kind of connect. Yes. Then exactly. Yeah. And so when we look at these guys, same concept, you know, exact same concept. Okay. So remember, you weren't here. We were talking about bond length, the difference between the hydrogen, the fluorine, and so the bond length between hydrogen and chlorine. Chlorine is a longer bond, so it provides more area for it to interact with things. Okay, because the atom is bigger and okay. So we've already talked about hydrogen bonds and their effect. The more hydrogen bonds, the more it's going to take to sit there and break it apart. So if we have a, say we have a multiple alcohol, something like this. Compared to okay, which one would we expect to be more, have a higher bullet? Okay, this one, this one. Okay, first one. Okay. And that's because of the hydrogen bonds. The more hydrogen bonds you have to. Okay, so hydrogen bonds are going to be forming between the nitrogen and the hydrogen, or the fluorine and the hydrogen, or the oxygen and the, you know, so hydrogen bonds basically have the hydrogen present. So it's something that's strongly electronegative, and then hydrogen, right? That's a good question. I think the 2 would win because there's 2 points of interaction compared to that single 1 point. Yeah, I think so. That would be my logic. So the more, because they're cooperative. The more hydrogen bonds you have, the stronger it is. So, like for instance, our DNA doesn't just separate at room temperature, right, or at 37 degrees, because it's a lot of points, a lot of hydrogen bonds connecting it, right? So it makes it a lot harder at that point. Yeah. Yes, exactly. You have more of that red area because it's cumulative. Yeah. It's a good way of looking at it. Yeah. Okay. Yeah. Yeah. Because remember, fluorine is really strong, oxygen is really strong, nitrogen is really strong, and then everybody else is just kind of, a little bit weaker. So. Okay, so we've already talked about hydrogen bonds between water. We've talked about this several thousand times. So it goes back to that thing, right? Partially positive, partially negative interaction. So this hydrogen that's partially positive is interacting with oxygen that's partially negative. And that's what kind of keeps it together, right? It gives it that order that we want, right? Okay. So hydrogen bonds in your primary amine is going to be stronger than that of the secondary amine. Why is that? Primary bonds in a primary amine is going to be stronger than a secondary amine. Why is that? Because it has more hydrogens to attach to. You have your hydrogen bonds that'll be forming between here. Compared to with your secondary amine, you have a hydrocarbon here, right? So the only thing that you have in terms of your hydrogen bond is this one. So your other ones are just dipole. Make sense? Okay. And then that's clearly the tetraamine. It doesn't have any hydrogen bonds because there's no other hydrogen for the nitrogen, right? So it's not going to form a hydrogen bond. It doesn't have one, right? Okay, so we'd assume that something with that's a tetraamine is going to be lower than something that is a secondary amine or something that is a primary in terms of boiling point. Okay. So this is in protein. Protein is a good example. Protein has quite a few hydrogen bonds that are formed. And so that hydrogen bonds allows that curl form in the secondary structure of protein. Okay, so that's just showing hydrogen bonds forming between one amino acid and another amino acid. In DNA, we have 2 hydrogen bonds between the A and the T. We have 3 between the G and the C. And so this is just showing you the hydrogen bonds existing between that. And that's, again, why our structures, our proteins don't denature. So, at 37 degrees, because of that secondary structures, those hydrogen bonds act support, and they're cooperative. So it's kind of like, so even though a hydrogen bond is like a fist bump, right? But you have a whole bunch of fist bumps that are coming together. And the more fist bumps you have, it really slows down somebody who's trying to play like Red Rover and run through you. Even though you're not connected, there's a whole bunch of these guys in the way. It'll slow that person down until they can't get through, right? And that's essentially what happens with like denaturing DNA strands. So, okay. Okay, so now let's talk about these shapes and their properties and how they affect the physiology, right? Our physiology. Okay, this is called salicylic acid right here. This is acyl salicylic acid. If you take a look, what is the difference between this guy and this guy. What was that? Okay, different numbers of hydrogen bonds, but look at also the structure. What was that? Okay, there's another oxygen. So we have this oxygen here, right? And then there's this other oxygen that's here. So we have another, this guy's called a carbonyl, right? Because you have the, so carbonyls. Okay, so basically you have an ester between the ring, right? So instead of having alcohol here, you have an ester structure that has a carbonyl that's sitting off the end. Okay, this here is this is an ester as well. So we have an ester attached to it. The O carbonyl double bond, where it's attached to another. Okay. Okay, and if we take a look at this guy here, this is acetaminophen, right? The distinction between this guy, one of the distinctions is we have an amine group, right? It's the location, of course. And then instead of having oxygen there, we have nitrogen. Okay, here. Sorry. This is ibuprofen. I don't know exactly what it's used for, but I'm assuming it's a medication that is treated for migraines, but not 100% sure on it. And then we have ibuprofen, right? So you guys are familiar with this guy, and actually you guys are familiar with this guy, Proxen. Okay, and Tylenol, right? So you're very familiar with all three of these, right? Okay. So if you look at these, all of these guys, all these drugs are able to bind to very similar receptors. Their effect on the receptors are quite different. So the effects of acetaminophen or Tylenol compared to ibuprofen, right? So ibuprofen, it helps with swelling, it helps with other things. It doesn't have, well, it does have an effect on your gut, but nowhere near as much as acetaminophen does, right? So because of these drugs, they have different London forces, they have different dipole moments, and they have different hydrogen bonds. Their binding to the receptors are going to be different. It's also going to tailor the receptors that they actually bind to. They bind to two different receptors, but they have very similar effect. And there's an overlap of one receptor that these two guys can bind to, that which basically recognizes the amine structure and the carbonyl. Okay. So melting point has very similar effects as well too. Okay, so but the melting point is also going to be affected by how things pack, right? So this here represents the number of carbons on the atom. So if we have an odd number of carbons, even number of carbons, if you have an odd number of carbons, we can see that the melting point of the even number of carbons is going to be slightly better than what you have in the case of the odd number of carbons. And that is partially due to how these guys will pack with each other. So odd number of carbons tend to pack end to end, where an even number of carbons, they're going to have some overlap. And that overlap causes that slight increase, that little bit of overlap. So odd numbers are going to pack less tightly, where even numbers are going to pack tighter. Solubility. Okay, so this should be kind of straight. Oil and water. When we think about oil and water, this is going to be very important from here on out in terms of extractions and everything like that. So, does oil and water mix? Why not? One is polar and one is non-polar. Okay, so if I have something that is a hydrocarbon and I put it in a mixture of oil and water, where am I going to find that hydrocarbon located at? What was that? Tell me. Okay, hydrocarbons are non-polar. Are they going to? Okay, so they're going to dissolve in oil. Okay, okay, so like dissolves like. So oils are going to, which are all hydrocarbons, they're going to dissolve hydrocarbons. So we're going to use solvents that are hydrocarbons to sit there and collect hydrocarbons. So the more nonpolar you are, the more you're going to be in the oil phase rather than in the water phase or the polar phase. The more you're going to be in a non-polar phase than the polar phase. Okay. The more polar you are, the more you're going to be in the water, right? Or the polar solvent. Okay. So no, there isn't. No, there isn't. I mean, if you're polar, you're going to be in polar. If you're non-polar, and this is one of those things that we're really lucky, but we get some things that are polar and non-polar. What they'll end up doing is being at the interface. Like for instance, you guys know your cell wall. Your cell wall has a polar head and a non-polar tail, right? So because your cell wall has a polar head and a non-polar tail, if we isolate it, it's going to sit at the interface, right? And so you're going to get a nice little layer where water's going to be on top and the oil is going to be on the bottom, and then you're going to have this little white layer of all the cell debris that is your cell membrane that's been separated. Does that make sense? Okay, so this is really cool because then you can use this particularly for isolation of organic compounds, because some organic compounds are going to have polar moieties and then others are not. So depending on the phase that you're working with, you could actually separate it in phases, right? So you could have that intermediate phase. So depending on your solvent, you could sit there and have a nice separation. So if we have something that is, we have water, we have, let's say, butanol, and then we have butane, or not, let's say heptane, because heptane is a liquid, right? So then if we use all three of those together, we could sit there and separate the ones that are really polar would go in the water, the ones that are somewhere in the middle would go in the butanol, and then the ones that are totally non-polar are going to go in the heptane, right? And so then you could just isolate those phase and isolate that moiety and only that moiety. Okay, does that make sense? Okay, so this is going to be really important later on when you guys actually get into the nitty-gritty, hopefully this week. So, okay, I have to look at the lab that you guys are doing first. So, okay, so this is just basically showing you that, right? So if this guy is partially positive and partially negative, so the negative, the oxygen, the partially negative of the oxygen is going to interact with that partially positive, and the partially positive is going to, the hydrogen is going to interact with that partially negative of our compound or our molecule. Okay. Mm-hmm. Mm-hmm. Yep. Yeah, because if you look at soap is a long chain of hydrocarbons, but you have the other side is it's polar, right? So you have a polar head and a long carbon tail. So the carbon tail will interact with anything that is greasy and everything like that and surround it. And the polar head will act with anything that's polar. That's right. Yep. Yes. And so that's typically what happens with cell membranes, right? Of bacteria cells. When you wash your hands and everything with bacteria cells, you're breaking apart the cell membrane that they have. Okay, but they also have what the cell wall in a lot of cases. So they have another layer that's like glycans and stuff like that. But usually there's pores that allows things to go through. If you wash your hands long enough, you get through those pores and then you break down that. Okay. Okay, so this kind of gives us an idea. So the oxygen here basically can drag these guys into water. So in this case, this guy is called what again? It's called what? An ether? What type of ether? It's diethyl ether. Okay, is it diethyl or dimethyl? Dimethyl. Okay, so this guy's dimethyl ether. So dimethyl ether is soluble in water. Makes sense because we have that oxygen there. You don't have such long chains that you're affecting. Okay. This guy, ethyl methyl ether, is soluble in water. As we start to get diethyl ether, that's only slightly soluble in water. As we get bigger, this is ethyl propyl ether, minimally soluble in water. And then as we get dipropyl ether, non-soluble in water. Okay, so as those chains on the outside gets bigger, that oxygen has less and less impact. Okay, because the surface areas of those chains are outweighing the oxygen, the polarity of that little oxygen that's there. Okay. Okay, so THC, marijuana. Okay, so marijuana has this, okay, this here is the nonpolar tail that's going on here, but you have this polar moiety, and slightly polar moiety that exists here, right? So it's because you have just this guy and just this guy, but you have a lot of hydrocarbons surrounding it. You do better at isolating THC. We'll isolate in water, but it isolates poorly in water, right? So it's isolated better on in an oil base, right? So if we talk about our blood-brain barrier, which basically is a barrier that is made with, it's like a cell wall with hydrophilic heads and long hydrophobic tails, but is multi-layer. So in this case, things that are absorbed by fat so drugs that can be absorbed by fat or fat soluble are going to be easier to get through. So the reason why we get high pretty well when we smoke, or if you smoke, or if you take THC, is because it goes through that membrane. And so you feel that effect because it's able to get through that blood-brain barrier. Okay. So in this case, both of these guys, THC more effectively is able to cross that blood-brain barrier, and barbiturates are able to also cross those blood-brain barrier, things that people often use to get high, right? Okay, so you take a look at halides. So we have, this guy's pretty soluble, very, very soluble in water. And why do you think it's soluble in water? Because it's polar, that's right. And then we know that chloroform is soluble in water, okay, because it's polar. Then we get, let's see, bromomethane it becomes less soluble. Bromo, what's that? Iodo. I'm sorry, it's iodo methane. Okay, it becomes less soluble. And why is this less soluble, even though it's a halide? Yes, because it's larger and less polar, or less electronegative. Thank you. Long day. Okay, and then we'll notice as we get longer, the chains get longer. Still soluble, but it's not very soluble, right? If we get even longer here, it becomes slightly soluble. If we get even longer, it becomes insoluble, right? Even though you have that fluorine available, it's not going to be able to counteract that long chain. So eventually you're going to get to the point where that dispersionary forces are going to cancel out just that one dipole interaction. Okay. And that's pretty much what you want to take away from this, right? So eventually you're going to get to the point where that long hydrocarbon chain is going to make sure that everything is soluble in oil rather than soluble. Okay. Does that make sense? And again, when we talk about solubility, we're talking about the solubility in water in this case. So in this case. Okay, how are you guys doing at home? Great? Horrible? Are you awake?
Overwhelming.
I'm doing really good.
Really good? She had a little too much THC, that's what it was. No, she has a natural high. Okay, so let's go ahead and take a 5-minute break, PP break, and then I'll see you guys back in 5. Okay, so let's get started back up. Okay, so like for instance, we've been talking about the cell wall, right? If you look at the cell wall, there's the phospholipid structure. Phospholipid is composed of a polar head. So this is the phospho part of it, right? And this part here is all polar. The whole thing is polar. Where the carbon chains, these are just going to be long chains of carbon, hydrocarbons. Okay, this here is a glycerin molecule that's connecting all of it. So your fatty acid chains are going to be essentially here. Okay, and so this part here, all of these parts here are going to be hydrocarbons. These guys represent that polar head. Okay, make sense? And so our cell membrane serves as a great barrier from keeping polar moieties from coming in, because you have the chains, the long, these are called, they would call them hydrophobic chains, because they don't like water. So they're going to be turned inside towards each other. The hydrophobic components or the non-polar components are going to be turned towards each other. I have to remember, it's like chemistry versus biology. So non-polar parts here, they're all interacting here. The polar heads are going to be facing the water. So things on the outside, like the water or anything polar, is going to stay out here. They're not going to be able to pass through here unless they enter a channel, okay, which is often regulated. So the cell membrane acts as like a, what is it called? The guy at the door, doorman. It acts as a barrier. What is the doorman called? He's called the guy who checks your IDs and everything like that. Bouncer. The bouncer. He acts like a bouncer. It's been a while since I had to teach bio, so general bio. Okay. So we're able to sit there and he lets things go through that is able to go through. Only thing that are hydrophobic or non-polar are able to go through the membrane. And there's only certain fat things that are able. If it's too big, it'll actually get stuck in the membrane because it only interacts with it, you know. So makes sense. So that's one of the way it keeps things out. Yes, and it's funny because this class, organic chemistry, the second semester deals a lot with the bio component. So. Okay. Now, since we're single bonds, right? These are single bonds. These bonds are rotating. So you have your kit. Can you do me a favor? Make a a methane molecule. And you guys get in the habit of bringing your kits. We're going to do a lot of modeling because this is going to help. Believe me, it's going to help you visualize it. So eclipse is when it's eclipsing each other. And so since it's a single bond, you're able to rotate about freely. Okay? So that's going to be kind of important. So that's, kind of gives us a lot of flexibility in terms of what we have because everything is kind of rotating now, right? So what we do often when we do our drawings, we have to represent this so that we can see that it's able to rotate and that things are staggered or eclipsed. So we draw what we call a Newman projection. This is a Newman projection where this represents the hydrocarbons, right? And then you can see the hydrogens in this case where this guy would be our staggered conformation and this guy would be our eclipsed conformation. Okay, and the difference between those is 60 degrees. So a 60-degree turn will allow one to be staggered and the other to be eclipsed. Okay, so Newman projections is drawn like this. Okay, so now this becomes important when we start talking about other, let's say we have halides here, right? Let's say we substitute one of those hydrogens with a chlorine or a fluorine. I think fluorine is green, if I remember correctly. Just add a chlorine to take off a hydrogen and remove a chlorine. And add a chlorine, sorry. So you take a look at that. Now, under both circumstances, show me an eclipse situation. Okay, so you have an eclipse situation. Okay, eclipse situation. Now, eclipse, because you have that location where you have the hydrogen on one side and the hydrogen on the other side, or in this case, the hydrogen and the fluorine, that's a lot of energy. A lot of energy associated with that, right? Because they're eclipsed to each other. If we switch them that 60 degrees, that's going to be less energy. Okay, so again, when we think about energy, we want to try to keep the lowest possible energy. So that staggered position is going to be favored over the eclipse position because of the energy. Okay, so staggered is going to be more stable than eclipse because of the energy. Okay, and so you kind of see also in terms of projection, it's a lot easier to see what's going on in the case of the staggered. You can clearly see that fluorine in the back row if you're looking at it from one end compared to the other, right? So again, lower in energy, right? Practical purposes as well as in reality, right? In terms of the structure itself. Okay, so as we were sitting there looking at that structure, right? So if we sit there, we think about it. So we have that bonding and then anti-bonding orbital, right? The bonding and anti-bonding orbital. That staggered conformation, it causes what we call a hyperconjugation, which allows stability between the bonding and the anti-bonding orbitals. So do you guys remember when we talked about pi bonds, sigma bonds, and we have sigma bonding and we have a sigma anti-bonding? So this pi represents that hyperconjugation that will allow that bonding and that sigma bond, the anti-bonding and the bonding of the sigma bonds to be stabilized. Okay. Okay, so you did your rotation, and if you do your rotation, if it's eclipse, what happens? Exactly. So if you start looking at it, he actually has a really good example here. So look at the hydrogen off of the third carbon. If we off of your third carbon, how close it is to the hydrogen off of the first carbon, right? If it's eclipsed. Yeah, they're like right on top of each other, right? So that's an issue, right? It's not good for us ultimately. And so the staggered conformation is going to be better in the circumstances because of that, because you want to maximize the ability of those hydrogens interacting with each other, right? Minimize the ability of those hydrogens interacting with each other. So if you take a look at it, you're going to have staggered moieties on both to make your life a lot easier to prevent those interactions between those carbons that are coming off the hydrogens that are coming off those carbon chains. Okay. So when we do Newman projections, we always put the carbon with the lowest number carbon in the front, and then the carbon with the highest number towards the back. So if you take a look here, so this is our first carbon. This represents our first carbon. The second carbon is that represents the 0 towards the back. This will be your third carbon coming off of here and your fourth carbon. Okay. So, and this represents that same drawing of what you guys have there. Okay. Okay. So let's take a look. So if we start rotating if we rotate it around that first and second carbon initially, have it staggered. So if we start rotating the third and the second and the third carbon, so if they're right on top of each other, then 0 angle, that would be our point A. That would be the highest potential energy, which is not what we want. We want low energy. This here would be point B, right? That'll be pretty low, right? But not the lowest. This is point C. That's when we're slightly off, right? This here is point D, where you have your third and fourth carbon. Right, third, fourth. Yeah, your third and fourth carbon in opposite orientations, opposite of each other. So your Newman projection is. And so, do you guys take a look? So if you do that, take a look at your projections, right? Look at them from each of the carbon angles. And so, can you see the staggeredness between the first and the second carbon, and then the second and the third? Okay, so this is going to give us our lowest energy, right? Because they're not going to be interfering with each other that much. Okay, and we want to minimize energy ultimately. Okay, so because we go for that staggered, that's why we show this chain as zigzag, right? To help us recognize that staggeredness. Okay. And so ideally, we want to try to keep the furthest distance possible from each other, right? Our bond angles. We're going to try to be as far as possible as we can get. That's right. Exactly. There's social distancing. Good job. Nice analogy. I like it. Okay. So here, this is showing you the bond angle of a planar cyclic alkanes. So if you guys can do me a favor, make a cyclopropane. Cyclic propane. It may take a little effort. You may actually have to use 2 small and 1 big to make it work. There you go. Okay, now this is going to be really, really important for multiple reasons because you guys are actually doing it. So show me yours. Okay, so that's what a cyclic propane looks like, right? If you look at the bond angles, right, that's going to be like a 60-degree bond angle between them, right? That's pretty damn tight. So there's a lot of stress being put on that bond or strain. Okay, so tons and tons of bond strain put on there. Can you guys see the strain being put on there? You can visually see the strain put on there, right? Yeah, okay. So the further the bond angle, the less strain that you have on it. Okay, so do me a favor and do a cyclic butane. Cyclobutane, not cyclic. Cyclobutane. Okay, although the strain has improved, there's still strain on it. You guys can actually see it in this context. Can you not? Okay. How about a cyclopentane? Good. So can you guys still see the strain? Okay. Not as bad as it was with the butane, a little more improvement. Okay, and then go with a hexane, one more. Okay, so as we went and we looked at the bond angle, the first bond angle in the cyclopropane bond angle in the cyclopropane, this guy, ooh, cool, fades. So this guy here, the bond angle was 160. So if we think about it, tetrahedral is like the ultimate best thing for carbons, right? If it's a tetrahedral, what is the bond angle for a tetrahedral? One what? No. 109. 109 point, now I don't want it to erase. 09.5. Okay. So all of these guys are below 109.5. Only the one that is the 120 that's above 1.5. So the angle between these guys are 120, 120, 120. So furthest distance apart, right? That's what we want. Okay. Here, this guy's at 108. It's kind of close to that 109. It's acceptable. This guy is the more stable structure. Right? Although these guys do exist, they will exist, you know, but there's a lot of tension associated with it, or stress or strain. They call it angle strain. What was that? It's more stable, yeah. The other ones, they exist, they're stable, but there's strain that's being put on them. Okay. So this here represents that angle strain. So if it's less than that 105, you're going to have poor overlap. So your bond is going to be weaker. So it's going to be more likely to get clipped or attacked, right? Because of the strain that's associated with it. Okay. So in the context, when it's with things that are going to react, that's going to be the point that it's going to most likely react if there's options that you need. Does that make sense? So if we draw our, in this case of the cycloprotane, these guys are eclipsed, right? You don't have too many options here. You don't have that be able to spin the way that you would normally have to be able to spin, right? You're limited. Okay, because of that, less stable. Okay. So our cyclo butane, we can kind of twist them out of the plane, right, to help minimize that angle strain. So it's less, it has less angle strain than cyclopropane. Cyclopentane, we could twist out again. And it's going to have less angle strain than cyclobutane. And then here, this is our cyclohexane. If you kind of twist it out a little bit, you can get your structure where it's alternating and fitting beautifully. So then you can get that nice staggered conformation, and then you can be what they call strain free. Yes. And so you're going to be able, you need to be able to draw the Newman projections. You should be able to draw this too, right? Although I'm horrible at drawing it. You see my drawings, right? So, yeah, but this is the ideal formation, right? It being altered, you know. Okay. And you wouldn't have to put all of the hydrogen since it's all, you understand that those are there. Okay, so to draw your chair conformation, what you're going to do is you're going to start off with two parallel lines halfway between one another. And then you're going to put V's at the end of those. So B here and a V on top. Yeah, see that? So there's parallel lines here, there's parallel lines here, and there's parallel lines here. Okay. Signifies a carbon, right? Each corner would signify a carbon. It's one carbon, that's two carbons, three carbons, four carbons, 5, and 6. No, this is called the chair conformation.
Chair.
This is chair, as in I sit in my chair. Okay, so this guy is the Newman projection. Newman projection is when you have things overlapping each other. So the first dot there, that represents the first carbon. The round circle, that represents the second carbon. Okay, so the first dot would be the carbon that's closest to us. The round circle would be the one that's furthest away. So that's why they write it 1. This is 2. Okay, and then there's 3. What was that? Yeah, that's right.
So automatically when we see a model like this that has like a square like a circle, in the between, that will be a Newman projection.
Yeah, so Newman projections are a circle, a dot, see, and then you have like, there you go, things coming off. So this here represents the first carbon. The big circle back here represents our second carbon and things coming off of it.
Oh, okay.
Notice,
Got
okay?
it.
So this is a Newman projection. Okay, does that make sense?
Yeah.
The third carbon in this case would be, so here's 1, the 2 is back here, the third one is off the second one, right? So it comes off of here. That's our third carbon. This here, that's going to be in the circle, it's going to be our fourth carbon. Our fifth carbon is going to be up front. Our sixth carbon is going to be up front. Okay. So, do you see it? So, 1 circle, back here is our second carbon. Third carbon is right here, that indice. The fourth carbon is the circle, big circle. The fifth carbon is that dot in front. The sixth carbon is right here. I should say the indice in the front, the vertex in the front. Think about math, what is it called? Two things come together, the vertex, right? Do you see it? You have that look. a chair conformer. It only works for those that are like the hexanes, right? So it'll be hexane will work for them, and it'll work for, see, it'll work for even number ones, but not odd number ones. So it doesn't, well, pentane is just a square, right? I mean, sorry, no, butane is just a square. Hexane will work for that. Octane, it'll work for that. So. What was that? Yeah. Yeah, yeah, yeah. That's also what I wanted you guys to, because you can see it clearer with the actual structure. Okay. Chair conformer. Okay. So when you're drawing the bonds, you're going to be drawing bonds that'll be coming perpendicular, sort of to each other. Okay. So these are axial bonds. These are equatorial bonds. Okay. So these guys are going to come off like this. And these guys are going to go like up and down. Axial, equal, like equator. Okay. There, guys, on the other side. I didn't turn my camera on. Axial and equal. Can you guys see me when I show my face? I mean, show my hand movements.
Yeah.
Yeah.
Yeah, exactly. Yeah. So horizontal versus vertical. Yeah. Okay. So on the odd ones, we can actually do it on the odd ones, but it doesn't look pretty. It's going to be like two chairs coming together. Okay. So this works nice with the hexane, really nice. Okay. But when we get to the hexane. Hexane. I screw up. Hexane, yeah. So this is the hexane. And so this here basically shows you, they call them flagpole hydrogens because they're standing out, right? So this means that if we take a look at it, these guys are they eclipsing each other, or are they're eclipsing each other, right? So in this case, we can see them eclipsing each other this way and this way. Okay, so this guy is considered the boat conformer of cyclohexane. Okay, so this is called the flipped ring. Where's the other one? It's my original. So chair conformer, flipped ring, flipped ring, and that just shows you where the hydrogens are at. So we have them kind of interfering here. These guys are going opposites of each other. This guy is going opposite of this guy. This guy's out. These guys are opposite each other, but both of these guys are going in. Okay. So this is the flip ring. Okay. Boat. So basically, you have two elliptic parts of the ring. Okay. Now, if we take a look at these all together, so chair, lowest conformation. This is half chair. This is their twisted boat. This is your boat. This is your twisted boat. This is your half chair. That's your chair, right? So these guys would be those flipped. Okay, highest in energy. Okay, flip ring. These guys are going to be more stable. Why is this guy going to be more stable than having it on top or on bottom? So why will equitable positioning is better than axial positioning? Okay, it has to do with energy. So if we take a look at these guys, if we spread out the hydrogens, right? Hydrogens can spread out top, bottom, and planar, right? So then in this case, if they're here, right, let's say in this position, if we have a hydrogen coming over in this direction, and that direction, right? So then we'd have hydrogens that would be interfering with these over here, anything that's coming over here, okay? So we want to minimize that interference, that crossover. Okay, so here, this is your equator substitution. Okay, and so you can kind of see staggered. Notice all staggered here, staggered, staggered, and then this guy is coming off, right? Where this guy would be our axial substitution, which would, you can see it's going to interfere because this guy's going to branch off this guy, interfering here and potentially with this guy. So less interference happening here compared to right here. So. Okay, here, this is 1,3 diaxial interactions. So in other words, if we're in this position here, we have two hydrogens that we're going to be interacting with, that we're going to run into their space. You know, it's kind of like, again, social distancing, right? So somebody gets up to you in the grocery store, don't have a mask on, they get right next to you, right? You're going to be like, hey, give me a little space, right? So, and then another person does exactly the same thing on the other side, and you're caught between two, you know, maskless individuals coughing and hacking all over you. Right? So you're gonna be like, hey, I need my space, right? So again, we want to think about it. If that's close, that's high energy, right? We want to try to get further away so we can get, you know, safe energy. We're not bumping into each other. Okay. So this is often called steric strain because you're sterically hindering the other, or steric hindrance. Okay. It's funny. Terminology changed quite a bit over years. So this hydrogen that's coming off of this methyl group here is going to be a steric hindrance to the other guy. Okay. So we want to try to prevent steric hindrance as much as possible, because that's high in energy. So the Gauchi is a 0.8 kilocalorie per mole, and it's less stable than the anti, where the Gauchi butane. This guy here is the acyl methyl cyclohexane. Again, steric hindrance here, right? This guy is going to be 1.5 more than the equator version. Okay, so this here is our equilibrium constants, and it's comparing our equator versus our axial, right? So the equilibrium constant is 1, the methane equal versus axial is 18. So that means that it's favoring the equator, right? So if the numbers go up, it's going to be favoring the equator. The smaller those numbers are, the less it has an effect. Okay. So are you guys with me? In terms of the equilibrium constant. Okay, so the difference between starch and cotton. So what happens if we eat cotton? Have any of you guys ate have any of you guys ate yarn? I mean, or not yarn, but thread. As a kid, I used to eat thread. Nobody's ever done that as a kid. You ate cotton ball when you were younger. You didn't swallow it. Okay. So what happens? And do any of you guys know what happens when you eat thread? Yeah, it comes out exactly the way it went in. So in my poop, I had like thread hanging off my poop and everything like that. And I got really constipated because I ate a lot of thread. Put it like that. So, and this was as a little kid, it wasn't as an adult, you know. So anyway, the point is that that bond, right, is different than starch. Starch we eat all the time, like potatoes. So what happens with potatoes and rice and what happens to that? We're able to digest it, right? So if I eat potatoes, it doesn't come out as potatoes, does it? But if I eat thread, it comes out thread. Go home and eat some thread and you'll see what I mean. Corn, yes, the husk of corn is the same thing, yes. The husk of corn. Come on, the only way you learn things is by doing it, right? Okay, now the difference between those is going to be your equator versus your axial, right? So they're both glucose molecules, but how they're connected is slightly different, right? So starch are are axial, and then cotton is equator. Starch, we break down. Why do you think we break it down? Easier. Why is it easier? They're both polar. They're essentially the same chemical structure. What is it? Equator versus axial. Which one is more energy? Are you sure it's going to be more energy? Axial is more energy. If we go back, right? So let's see, axial. Yeah, this one shows us nicely. So those are two diaxial molecules right there, right? Axial is going to be more energy, right? Axial, more energy. This guy is more stable, less stable, right? Axial. We're saying that the structure, okay, when I say more energy, I'm talking about the structure itself, right? So being in that structure is a sense of energy, right? It has potential energy associated. Okay, we want to try to keep it low energy, period, right? So if you're unstable, part of your instability may be your structure, right? So remember, like with we were talking about cyclopropane. Didn't you see the tension between wasn't it bending like really hard and everything like that? I mean, you could visually see the tension, right? And that's on your model. That's not even talking about in real life. So just imagine with bonds in real life, where you want to be at 109 is your optimal, your furthest part, your usually the shortest you're going to be from each other is like 109 if you can have that choice, right? You want to try to keep it that 109 being the closest you're going to be. But now you're at 60, right? 60 compared to 109 is a big gap, right? More stress associated with that. The more stress there is, aren't you going to be uncomfortable? Okay, put it like this. Let's say you're wearing really, really, really tight pants. Really, really, really tight pants, right? So if your pants are really, 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 really tight, is that going to be more energy kind of trying to suck it in and keep your belly from busting out? And isn't it uncomfortable, right? And that uncomfortable adds up to energy. How long are you going to be able to stay in those pants? You're going to stay in there for 3 days, or you're going to be able to stay in, where if you're in sweatpants, right? Your fat boy pants, right? If you're in your fat boy pants, then you can stay in those for like 3 or 4 days and not worry about anything, right? All right. until they get stinky. That's a whole nother set of issues. That's another whole nother set of energy levels that are associated with that, right? So the energy level that's associated with you staying in those pants, but you want to get out of the pants as soon as possible if they're really, really, really tight. They're way too small, right? And you're sucking in and try to keep them on, right? More energy, okay? So that's the same thing with these conformation. It's more energy to keep these conformation because they're running into things, right? That's causing energy, friction, you know? You want to minimize as much energy as possible. So you want to try to find a conformation that gives you the least amount of energy, okay? So here, being out this way is less energy. Now, if you're less energy, is there a reason for you to want to change? No, because you're like, fuck it, I'm good here, right? I'm in my fat boy pants, right? I don't have to worry about anything, right? But as soon as you're in those tight ass pants, you're like, oh, let me get out of these. I need to put on my shorts, you know, I need to get in my fat boy pants, right? Give me something, get me out of this, right? So if we think about it, the sugar, are we over? What time is it? We're doing good. I'm good. Okay. So here, because we have this equator component, we have equator going this way, we have axial going this way. Because of this axial component, right, we want to get rid of it, right? So we break it down. It's a site where we want to be broken down. So we're able to digest that one. Where these are straight equator. Those guys are going to be the furthest apart, right? They're not going to interfere with too many things other than the other one that's acting equator on the other side, right? Not too much. Where this guy is interfering with this oxygen this way, and they're probably interfering with the carbons that are hanging out here. And so it's like, you know, fat boy pants, too many things around me. I need to get out of it, you know? So those are going to be sites of cleavage, right? And so amylase will actually break this down. They'll cut these sites because that's the point where you don't want to break down. Okay, where in cotton, that's not the case. Right? That's right. It's happy. It's like, cool. I am cool. I don't have too many things that are bothering me. I'm good to go. Right? So. This one here. Here? Oh, you're talking about here. Over here? Yeah. So that's just this represents another like long chain of carbons that are attached. So if you look at it, here you have the hydrogen, this oxygen and this hydrogen, right? Compared to, okay, so you got these guys that are acting equator here. Here, these guys are acting axial. This guy's acting equator. So this guy is good here, right? But it's just this part here that's going to cause interference with the guy next to it over here. And then also the other hydrogens that are hanging off of this carbon, right? Which is, let's see, there's 1, 2, 3. So there's one other hydrogen that's going to be hanging off of here that's going to be bumping. And so you've got to take that in consideration here. And so this guy is cool, right? Because he has less things that he's bumping into. But the one that's going down is the one that's the issue. So these are going to be the spots of cleavage here, there, yeah. Okay, so to get your glucose molecules reformed. And so just because of that bonding is the distinction. That's the reason why we're able to digest one, and the other one is fiber. It goes right through us, right? Okay. Cellulose says the same way. Actually, so that's what cotton is, it's cellulose. So that's the reason why we can't digest it. So I've been doing, like I said, I've been doing experiments since I was 3, you know? So I learned the hard way. And for some reason though, I love chewing on thread. My mom, I would always eat her thread, and I always come out of my poop. Thought it was the coolest thing. My poop, look at my poop. It's like different colored poop. And, yeah. So. Yeah, because it's fiber. That's all it was. It was clearing me out, but it would get stuck because the threads would get kind of caught up along things along the way, so it would take a while. So I'd have poop that'll be, as it starting to come out, comes out and be stuck in my butt because it would be connected to another poop that's inside. And sorry, visuals, they serve a purpose, don't they? You guys will never forget this discussion, will you? Okay. Okay, so our next thing is cis and trans. Okay, so the term cis means like, kind of like, trans is across, right? So you're going across. Cis is kind of like sisters, yeah. That's a good way of remembering cis. Okay, so this guy's going down, this guy's going down. So those are considered to be cis of each other because they're both heading down. Trans, one going up, this guy's going up, this guy's going down. Okay, so that's trans. So they would be opposites of each other. Okay, trans, opposites, cis, same direction. Okay, so both of these guys are going down, down, and down. Does that make sense? Okay, so when we do nomenclature, we also have to take in consideration isomers of each other because those isomers play a part. This guy, cis 1,4-dimethyl hexane. So that basically means that both of those guys are going down or up. They're both going in the same direction, right? Either one doesn't matter, but they have to be the same direction. Okay. So trans 1,4-dimethyl cycling, opposite directions, right? Okay. So it's more than just, that general part of nomenclature. Now we have to think about how are they staggered. Are they staggered the same way? Or are they staggered the opposite way? Okay. Make sense? Let's get harder. Okay. So cis, same direction, right? So in this case, these guys are going to be considered both be going down. So if we flip them, equator, axial. So we're just kind of flipping their location. And then this guy would be trans, okay? So this is equator, and this is axial. Well, we know that axial is going to be less stable than equator. Equator is more stable. So this guy is going to be the more stable form. So this is going to be the preferred trans. These guys, they're just flipped. They have the same stability either way. Okay. Okay. Let's see if we can finish this up. We have 5 more slides. And then what we'll do on Wednesday, the beginning part, before we start the lab, we'll give you a couple of questions and we'll see how much you guys remember from today's lecture. How about that? Lab number 2. Yeah, lab number 2. On your paper, yeah. Yeah, I was trying to give you guys a little bit because I know we were going to get to it eventually, but I didn't want to give you too many. So, and then now I can give you 25 minutes. So, okay. So, first off, is this a trans or cis? Trans, right? Opposite directions. Okay, so if we take a look at this, these are both axial. Axial, you see they're going to interfere with the hydrogens that are coming off of both moieties, right? So this would have a 1,3 diaxial interaction, meaning that it's going to be able to interact with those carbons off that side, right? Which is what we don't want to happen. So is this going to be high in energy or is it going to be low in energy? This guy's going to be high in energy. So the best trans to be out would be equator, right? Because then it's not interacting with these guys. Okay. Okay, so we can get very complicated with that cis trans, right? So this guy is cis 1 tert butyl, 3-methyl cyclohexane. Okay, cis, meaning same direction, so cis. Okay, and then it could either, so if we look at this, we have one here, we have one over here. This is facing equator, this is facing equator on the side, right? So if we had them both on the same side, facing the same equator, this guy's going to be less stable, right? So this guy we have facing out this way, this guy is facing out that way on the corner. If we do a flip ring, this guy is going to be less stable. Okay. This guy is trans. Okay. So we have one that's going to be axial, one that's going to be equator, right? And then this is equator and axial. So this guy is going to be more stable. This guy is going to be less stable because you have these guys that are going to be interacting with these components. Where if we put it out here, you don't, this guy is equator, it's not going to be interacting with those components, but you have this guy heading up, although it can have some interaction, but it's minimal interaction with that compared to what you have here in this situation. Okay. And that, in all honesty, this is going to take a little getting used to, right? Seeing what is going to be more stable. Okay. Okay, so we can have ring structures that can be fused either cis or trans. Okay, so trans, cross, right? Okay, so in this case, these guys are going to be equator, giving us our nice little trans moiety for the hydrogen, where this guy would be cis moiety, axial, and equator. This guy's going to be less stable. This guy's going to be more stable. Okay, steroid rings. So this is the typical formation for our steroid rings. You'll notice these are 3 hexenes and then a pentane at the end. Okay, so this is cholesterol. And then we have functional groups that'll be hanging off of it. Okay, so these guys, these rings are going to be transfused, more stable. So we take a look how it's, you can see it, transfused. Okay. Questions, concerns, Kool-Aid, cockroaches. We're going to do practice on Wednesday. So I have a few questions that I'm working on. Slide, so.
See you Wednesday.
Okay,
Bye.
bye.